Hello, here we are in Chapter 8. We're doing matrix solutions to linear systems. So we're going to learn about matrices and how we can use those to solve the systems of equations that we have done earlier. So we have solved systems of equations already, but we've either used substitution or the elimination technique. Here's a new technique, and we're going to learn another technique after this one as well, but this one's using matrices solutions to solve the linear systems. But before we can do it, we need to talk about what a matrix is. So what we're going to do here is we're going to write the augmented matrix for a linear system. We're going to perform matrix row operations, use matrices and Gaussian elimination to solve systems, and we're going to use matrices and Gaussian Jordan elimination to solve systems. Okay, so these are only the four objectives. So the objectives are not that long, but the technique is going to take several slides to get this complete. So let's talk about what a matrix is. Now, matrix is singular. It's M-A-T-R-I-X. But plural, you remove the X and you put a C-E-S. So matrices is plural. So, but anyway, so matrices are used to display information and to solve systems of linear equations. A matrix, which is plural as matrices, is a rectangular array. The information is arranged in rows and columns and placed in brackets. The value inside the brackets are called the elements of the matrix. So let's look at a diagram of this. So this is what we call a matrix. And actually, this is what we call a 2 by 2 matrix because it has 2 rows and 2 columns. The elements are the numbers inside this particular matrix here is 1, 2, 3, 4. Now, 1, 2, the elements 1, 2 represents a row, that's row 1, and the elements 3, 4 represents row 2. And the column 1, 3 is the first column, and the elements 2 and 4 represents the second column. So columns are vertical and rows are horizontal, okay? Now, the first step in solving a system of linear equation using matrices is to write the augmented matrix. An augmented matrix has a vertical bar separating the columns of the matrix into 2 parts, or 2 groups. The coefficients of each variable are placed in the left of the vertical line, and the constants are placed on the right. If any variable is missing, you place a coefficient of 0 in there. So that is what we call an augmented matrix. Of course, it's better just to see a picture of what we're referring to here. So if you look at the systems of equations of 3 equations with 3 variables, the first one here, you have 3x plus y plus 2z equals 31, and we have x plus y plus 2z equals 19, and then we have x plus 3y plus 2z equals 25. So we've seen this before in a previous section. But to write this systems of equations as an augmented matrix, you take the coefficients of each equation and make a row out of it. So you have 3, 1, and 2, okay, because those represents the coefficients of the first equation. And then the next equation, x plus y plus 2z, those coefficients are 1, 1, and 2. And then the third equation begins with x plus 3y plus 2z, so you put the coefficients 1, 3, and 2 down. Now you put this vertical bar, and that vertical bar acts as a separator. And it's basically separating the main part of the equations with the constants. And the constants being 31, 19, and 25. So that is the augmented matrix. Now the next equation, you have x plus 2y minus 5z equals negative 19. So you take the coefficients. You have 1, 2, and negative 5. Now notice there's an x term that's missing on the second equation. You have y plus 3z. So there's no x, so the coefficients is understood to be 0. So that's why on the second row of the augmented matrix, we begin with a 0 on that second row. 0, 1, 3. And on the third equation, both the x and the y are missing. So both the x and the y, so that's the first 2 elements in that third row are 0 because the x and y are missing. And then we got a z, so the coefficient in front of that one is 1, so it's 0, 0, 1. And then, of course, that last one on the 4. So the right side of the vertical bar are equal to the constants. the numbers on the left, the 3 by 3 matrix on the left, represents the coefficients of the variables. Simple as that. Okay, so now how we're going to solve the equations, we're not going to work with the systems as we did before. We're going to work with the augmented matrix to solve the equation. So that's the goal here. And at the end of the day, that's what we're going to do. We're going to use the augmented matrix to solve these equations. And this is the main objective for this section. Okay, before we can do that, I need to give you some rundown of how to work with these matrices. Okay, a matrix has with ones shown in the main diagonal and zeros below it is called row echelon form. Say that with me. Row echelon form. So if you notice, the main column, the main diagonal with the one that had the most elements in the diagonal, 1, 1, 1, that's all ones, and zeros are below each of the ones. So the first one on the first row has 1, so there's 2 zeros that are below it. And then the one in the middle has a 0 below it. Okay? Now, what we usually call that is the lower diagonal. The lower diagonal has zeros in it, okay, with ones on the main diagonal. Alrighty? So that is what we call row echelon form. You're like, well, how does that help? Well, think about this. If the equation is in row echelon form, think about this. You have the last row, okay, gives you 0x plus 0y plus 1z equals 4. So what does that mean? That means z equals 4, doesn't it? Once you have z equals 4, you can plug that back into the middle equation to solve for the y in the middle. Of course, you would have to multiply 3 times the 4 because it would be 3 times z, right? So 3 times 4, and then that gives you the ability to solve for y. So the middle equation will give you the y. The bottom equation will give you the z. Then you use those two knowns, now they'll be known, to solve for the original x in the original equation. Okay? So that's why row echelon form is important, is because if we can get it in that form, okay, then we get the ability to solve for the 3 variables. All right? All right, so yeah, this matrix is in row echelon form. All right, so let's look at this matrix row operations. The following row operations produce matrices that represent systems with the same solution set. Now remember, if you have a matrix that represents the same system, they're going to give you the same answer. So the solution set is the same. So let's see what they are. Well, 2 rows of a matrix may be interchanged. This is the same as saying interchanging 2 equations of the system. So for example, you might want to change the first equation and make it the second equation, and you might want to take the second equation and make it the first equation. So that's interchanging 2 equations. The answers are not going to be any different. You're just reversing the order of them. Okay? The elements in any row may be multiplied by a non-zero number. This is the same as multiplying both sides of an equation by the same non-zero number. So what this is basically saying is something that you've always remembered. Whatever you do to one side of an equation, you got to do it to the other side of the equation. That's what this is basically saying. So if you multiply the first side, one of the equations times 2, you multiply the other side of the equation times 2. So if you've got a matrix row, and the row elements are 2, 3, and 4, okay, 2, 3, and 4, and you want to multiply that whole row by 5, you can do that. Because the numbers on the left are the coefficients, the number on the right of that vertical bar is what the constant, that's what that equals to. So if you multiply everything times 5, that's the same as multiplying one side by, and both sides by the 5. Okay? All right. The elements in any row may be multiplied by a non-zero number, and these products may be added to the corresponding elements in any other row. This is the same as multiplying both sides of an equation by a non-zero number and then adding that to eliminate a variable. Remember, we did that when we were solving systems of equations by the elimination method. We took one equation and multiplied it by a number, and got the opposites, and then we add them up to eliminate the variable. That's what this is basically saying. You want to eliminate the variable. In this case, it's not really eliminating the variable per se, it's more or less changing that coefficient to 0. So you'd want to do something like this. You want to multiply one equation or one row by some number, add it to the other equation so you can allocate a 0 in a certain location. You're like, why is 0 in a certain location desirable? Well, because you remember in row echelon form, there's 1s on the main column, there's 0s below it. So you might want to take those two equations on the top, multiply the top equation times some number, add it to the second equation, okay, so you can obtain a 0 in that first slot on that second row. Alrighty? And two matrices are row equivalent if one can be obtained from the other by a sequence of row operations. So if you got one matrix and you got another matrix and you're like, okay, can you go from here to here by these row operations? And if you can, then the matrices are equivalent. You're like, why is that important? Well, if the matrices are equivalent, the solution set for this matrix will be the same as the solution to this augmented matrix. So they'd be the same. So basically it allows you to go from one step to another step. So in other words, if that wasn't true, if you go from one augmented matrix to another augmented matrix and they're not the same, if they were not the same, then the solution set here would not be the same as the solution set here, so it does you no good. So you want the matrices to be, they want to be row equivalent, so you can say the matrices are the same matrix, so thus the same solution. And that's what we're looking for. Okay? All right, symbols for these row operations. So each matrix row operation is preceding list can be expressed symbolically as follows. If you want to interchange the elements in the ith row and the jth row, you use this notation. Ri has a double arrow back and forth, Rj. So if you have, for example, if you have R1 and this little symbol here that got the double arrow, R2, so this is, you would interchange the first row to the second row. So if you have R1 with this little arrow symbol and R2, what you're doing is you're looking at the augmented matrix and you're taking the first row, putting it in the second row, taking the second row and put it into the first row. And you're like, well, why would you want to do that? Well, maybe the first term on the second row is 1, but the first element in the first row wasn't. You remember you want 1s in that main diagonal. So if you have any row that has a 1 in that first one, that's where you want to place it because it's easier to work with. So that's the reason you would want to do that. All righty. Now, if you want to multiply each element in the ith row by k, then you have r times r of I, r sub I. So for example, if you want to take the second row and multiply it by 2 or 1/2, then you would take that number and multiply every element in that row. And that's what the symbol is saying. Okay? And then add k times the elements in row I to the corresponding elements in row j. So you have k times ri, like we had before, and then add that to rj. So basically a lot of times what you would want to do is you want to take the elements in the first one of the rows, multiply it by a number, then add it to the next row, and then the next row becomes that operation. So if you have, let's say for example, if you want to multiply the 2 times the second row and then add that to the third row, that result becomes the third row. Okay, and you're like, why would you want to do that? Again, you want to get zeros in certain locations. That's the reason. You want to get it in what we call row echelon form. Alrighty. So we're going to use this matrix 4, 12, negative 20, and then 8, and then 1, 6, negative 3, 7, negative 3, negative 2, 1, negative 9. Now remember, you can make this into a system if you want. The first row would consist of this equation. This is what it would be. 4x plus 12y minus 20z equals 8. Second row, 1x plus 6y minus 3z equals 7, and so on. Okay, so what we're going to do is perform the indicated row operation. We want to switch the first row to the second row. So R1 is interchanged with R2. That's how you say it. R1 interchanged with R2. Now, if you notice, well, why would you want to do that anyway? Well, look at row 2. Look at that first element on that second row. It's 1. Boy, I wish that first element in that first row was a 1, and it's a 4. So I could switch those if I want to. So if I do that, it becomes 1, 6, negative 3, 7, which was the second row. And then the second row becomes 4, 12, negative 28, which was the first row. Third row was not changed. Okay, so that's what that symbol means. You're going to interchange the first row with the second row. So, and the reason you might want to do something like that again, you remember you want 1s in that diagonal. And so the first element of the first row needs to be a 1. And it wasn't initially. So all I had to do if I just switched the row. So that's part of my work is done right there. Okay. Now perform the indicated operation of 1/4 times R1. So we're going to go back to the main one, our main matrix. So whether 4, 12, and negative 20 and 8 is the first row. And we're going to multiply it by 1/4. So it takes every element in that first row of the original matrix up on top and multiplies it by 1/4. So it's 1/4 times 4, 1/4 times 12, 1/4 times negative 20, and 1/4 times 8. Do the math. You'll get 1, 3, negative 5, 12. 2, sorry. 1/4 of 8 is 2. Okay? Now, you're like, why would you want to do that? Well, in this case, for a couple of reasons. One, it does put a 1 in there if you want to get a 1 there in that way. That's one of the reasons. But a lot of times people will multiply by like a fraction, like 1/4, to make the number smaller. Okay? If they're smaller, they're easier to work with. Okay? So a lot of times that's why people will multiply a row by a fraction, just to reduce the magnitude of the numbers. So if you notice 1, 3, negative 5, and 2 is a whole lot easier to manipulate than the original 4, 12, negative 20, and 8. The original row might require even a calculator if you've got to use it with another row. Now it's easier to work with. Okay? Now let's look at this example. Okay? So again, this is the original matrix. 4, 12, negative 28, 1, 6, negative 3, 7, negative 3, negative 2, 1, negative 9. That was the original matrix from the previous slide. And now what we're going to do is perform the indicated operation. We're going to multiply the second row times 3 and then add it to the third row. So 3 times R2 plus R3. And what we're going to do is we're going to put the result in row 3. So if you notice, now this is, before I go through this whole mess, look at the first row and the second row. They're not changed, is it? It's 4, 12, negative 28. We got 1, 6, negative 3, 7. So a lot of times I'll just tell people, if you don't change a row, write it down. Okay? You're changing the third row by taking the second row, multiplying it by 3, and then adding the third row. You're like, why would you want to do that in the first place? Well, let's see what happens. Well, 3 times the first element in the second row is 3 times 1. And then add that to the first element in this third row. So 3 times 1 plus negative 3 is 0. Again, we want zeros in that lower diagonal. So that needs to be a 0. That's why you might want to do that. Okay? And then, but you got to do that on all of them. Okay? So 3 times 6, because you got to multiply 3 times the second element in the second row, which is 3 times 6, and then add that to the second element in the third row, which is negative 2, and you get 16. Okay? And then you take 3 times the third element in the second row, 3 times negative 3 is negative 9, and add that to the 1 below it, which is negative 8. And then you multiply 3 times 7. So you got it on the other side too, see? So 3 times 7 is 21. And then add that to the negative 9 below it. And that gives you 12. And if you notice, that last row is 0, 16, negative 8, and 12. And those numbers are kind of big. So you might want at this point multiply everything on that one by 1/4 again. If you multiply that third row by 1/4 again, you'll get 0 times a fourth is 0, 16 times a fourth is 4, negative 8 times a fourth. So that's something you might want to do. But you got to remember, what's the end game? The end game is to put zeros in the lower diagonal, and then you have ones in the main diagonal. So 1, 1, 1, and zeros below it. That's row echelon form. Okay, so this is solving a linear system by using Gaussian elimination. So how do we do this? So if we're going to solve a linear system in 3 equations with 3 variables using Gaussian elimination, we want to write the system as an augmented matrix, and we learned how to do that. And then we're going to use matrix row operations, which was what we've been doing on the previous few slides here, to simplify the matrix to a row equivalent matrix in row echelon form. This is called Gaussian elimination method. So we want to put it in row echelon form, with ones down the main diagonal from upper left to lower right, and zeros below the ones. So it looks kind of like this. So the first thing is you want to make sure a 1. Now this is kind of the order that you kind of go with it, okay? So you want to make sure you do a row, one of the row operations to make sure it's a 1 on the first element in that first row in that first column. You want a 1 that's in that red. That's where you want it. And you're like, well, how do you do that? Well, you might already have it. It may already be a 1 there. You don't have to do anything. But maybe the one, that one maybe is a 2 and there's a 1 below it. Maybe in that case you might have to switch 2 rows around, so the first one would be a 1. Once you do have that as a 1, then you use row operations to make zeros below it. So as you can tell, it may take 2 or 3 steps just to get to that second augmented matrix. You may have to switch some rows, and then you may have to add 2 rows. You may have to multiply the first row by something and add it to that equation to make a 0 below it. So you got to have zeros in below those. So that, like I said, this could require up to 3 steps just to get to the second augmented matrix here. Then you want to make the third augmented matrix. You want to make that 1 there. Okay, and at that point, you can switch rows with the 1 below it if you need to, or you can just divide by that term to make it a 1. Okay, so you need a 1 there. The next step is to make sure it's a 0 below it. Okay, so maybe you probably had to add the second equation to the third equation after you multiply by something, and then add them up and 0 becomes there. Then the fourth augmented matrix, you need to make sure there's a 1 there. And you're like, well, how do you do that? Well, you just divide by whatever is in that position on the prior matrix. So for example, if it was 0, last row, if it was 0, 0, 2, 6, if that last row was 0, 0, 2, 6, and you want a 1 there, then you got to divide everything by 2. Be 0, 0, 1, 3 then. So that's how you do it. So then you write the systems of linear equations corresponding to the matrix in step 2 and use back substitution to find the system's solution. Okay, so what that basically means is once you get to that last augmented matrix, you get what z equals to. So z would, remember I said z 1, 0, 0, 1, 2, okay, or 0, 0, 1, 3 I think I said, and so z equals 3. Then you use back substitution back in the original system to figure out what y is. And then you take the y and the z in that second one and then go back to the beginning. So it's kind of funnel back up towards the top is what you're doing. Alrighty. So what's the main objective here? The reason you want to put it in row echelon form is because that last row, this is the one I'm about ready to say, that last row in augmented matrix in row echelon form determines what z equals to. And then once you got what z equals to, you go to the middle equation to solve for the second variable. And then after you do that, go back to the first equation to find the first variable, and there's your ordered triple. So that's how it works. Okay, so let's look at this one. So we're going to use matrices to solve this system. We've got 2x plus y plus 2z equals 18, x minus y plus 2z equals 9, and then x plus 2y minus z equals 6. Now remember, we solved this another way previously, but we want to use matrices, and we're going to put it in row echelon form to do it. Notice it takes 3 slides. So here goes. So we want to write the augmented matrix to the system. So 2, 1, 2, and then the 18. And then 1, negative 1, 2, 9. And then 1, 2, negative 1 is the coefficients of the third equation. And then on the other side, there's a 6. Now, what we're going to do, we're going to use row matrix operations to simplify the matrix to row echelon form, with ones down the main diagonal from the left to the lower right, and the zeros below it. That's what we've been told to do. So what we're going to do first is we're going to switch the first row to the second row. Yeah, why are we doing that? Because if we switch the first row with the second row, we'll have 1 in that first element slot, which is what we're desiring. That's what we want. We want a 1 there. You know, could you switch the first row to the third row? Yeah, you could do that too, because there's a 1 down there as well. So you don't have to do row 1 interchange with row 2. You could have done row 1 interchange with row 3 if you particularly wanted to do that. And you're like, how do you decide? There is no really right answer to that question. You know, you just pick which one of you want. Okay? So then step 2, okay, so we've switched the first 2 rows, okay? Now what we're going to do is we're going to replace the second row by multiplying the first row times negative 2, add it to row 2. So the row 1 doesn't change. It's still 1, negative 2, 2, and the 9. It's still that row. And then what we're going to do is multiply that row times negative 2 and add it to the second row. So negative 2 times 1 is negative 2 plus 2 is 0. And then negative 2 times negative 1 is 2 plus 1 is 3. And then negative 2 times 2, the third row, the third element in that first row, negative 2 times 2 is negative 4. Add that to the element below it, and that's going to be negative 2. And then negative 2 times 9 is negative 18, and then add it to the 18 below it, and that's 0. And if you notice, the third row does not change. We're only working with 2 rows at a time here. So the 1, 2, negative 1, and 6 is the same. If you notice, the first row didn't change. So the first row didn't change, and the last row didn't change in that middle augmented matrix, that one in the middle. The only one that changed was the second row, because we wanted a 0 on that first element. So to do that, we multiplied every element in the first row times negative 2 and add that result to the element below it in the second row, and that becomes your new row. So now the new row is 0, 3, negative 2, 0 in the middle. So I got my desired 0 that I wanted. Now, do you see the 1 below that one? Okay, I want to get rid of that 1 and make it a 0 as well, and that's what we're going to be doing here. So what we're going to do is replace row 3 by negative 1 times row 1, and then add that to row 3. So if you take negative 1 times 1 is negative 1, add it to the 1 in the third row, you'll get that 0 that you're desiring. And then negative 1 times negative 1 on that first row is 1. Add that to the one below it, and that's going to be 3. No, I say below it, I mean down in the third row. And then negative 1 times 2 is negative 2. Add that to negative 1, you get negative 3. Then you multiply negative 1 times 9, which is negative 9. And then add that to the 6, and you get negative 3. So basically, you're taking the first row and multiplying by negative 1 in each individual term. You add it to the term below it in the third row, and that becomes your new third row. So these are all row equivalent. So understand, the solution to matrix, the first augmented matrix will be the same as the solution as the second augmented matrix, which is the same solution as the third augmented matrix. They're all going to give you the same answers for the x, y, and the z. Okay? So now we're at the 1, negative 2, 1, negative 1, 2, 9, 0, 3, negative 2, 0, and then 0, 3, negative 3, negative 3. So now what we want to do is we want to take this, the second row, and I think what it wants us to do, take the second row and the third row and interchange them. So the second row becomes 0, 3, negative 3, negative 3, And the second row becomes the third row, 0, 3, negative 2, 0. And then what we're going to do is take the second row, the new second row, and multiply it by 1/3. And you're like, why do you want to do that? Because we want to make that 3 there a 1. So 0 times 1/3 is 0. 3 times 1/3 is 1. 1/3 times negative 3 is negative 1. And 1/3 times the other negative 3 is 1. You might ask, why didn't they just do the first? Why didn't they just do the original 3? The 3 on that second one. Well, it's because it was a negative 2. So the reason they switched it was because originally the second row was 0, 3, negative 2, and 0. If I multiplied that one by 1/3, I'd get my 1, but then you'd have to take negative 2/3 times 1/3, and you get fraction. And we try to stay away from fractions. It's doable, and it's okay to work with them. They're just hard to work with. So we try to stay away from them if possible. So now you got the first row have a 1, 0 is below it. You now have on the second row a 1 in that main diagonal. So what's our next thing we need to do? That 3 on that third row in the middle, it needs to be a 0. So I take the second row, okay, take row 2 and multiply it by negative 3, and then add it to the third row. So 0 times negative 3, add to 0 is still 0, so that doesn't change, that's good. And then the 1 on that first, the second element in the second row is a 1, multiplied by negative 3, which is negative 3, and then add it to the 3 below it, and that gives you the 0 that you're desiring. And then negative 3 times negative 1 is 3, and then 3 plus a negative 2 is 1. And then negative 3 times negative 1 is 3, plus the 0 is 3. And notice, we got something else that's kind of nice. On that last row, we got 0, 0, 1, 3. We know what z is, don't we? Z is 3. So write the system of linear equations corresponding to the matrix. Once you get in row echelon form, here we're going to go backwards, okay? So the first equation becomes x minus y plus 2z equals 9. Then we got y minus z equals negative 1, and then z equals 3. So that augmented matrix here on the left was the augmented matrix that I ended up with right there. So it's the same augmented matrix on this slide here, and then I changed the augmented matrix back into a system that we were used to. And you're like, isn't this the same that we've done already? Yeah, it is. It's just a matter of we don't have to work with the variables as much. That's what basically it boils down to. You're not having to work with the letters each time. You don't have to deal with the x, y, and the z each time. You're just dealing with numbers. Okay? So we have z, and it's 3. So we put the 3 back into, so we filter it back up to the top. So we know y minus z is negative 1, but z is 3. So it's going to be y minus 3 equals negative 1. And that makes y what? 2. And then we put 2 back into the y in the top equation, so we filter it back up. So it's going to be x minus y plus 2z equals 9. Y is now 2 and z is now 3, right? So we put those back in and solve for x, and x is 5. So it's once you get the last variable, you use the middle equation to find the second variable, and then use the middle equation and the third equation to solve for the first letter in the equation, x. So the solution set is 5, because that's what x was, y, which is 2, and z is 3. That's an ordered triple. Okay? So that is what we call Gaussian elimination. Gaussian elimination. Okay? So it uses row echelon form. Remember, row echelon form is ones in the main diagonal starting from upper left to lower right, and zeros in that lower diagonal. So that's what we got to shoot for. Okay, so that's the Gaussian elimination method. Now, solving systems using the Gaussian Jordan elimination method. Now, this is just basically the same thing, but what it is we're wanting the ones in the main column. We want zeros in the lower diagonal, but you know something else? We want zeros in the upper diagonal as well. So basically you have a matrix that has ones in that main diagonal, but zeros down in the lower left like we've been doing, but zeros in the upper right as well in that 3 by 3 matrix. So what you do, let me give you the technique here. It says write the augmented matrix for the system. Okay, we're going to use the matrix row operations to simplify the matrix to row equivalent matrix to reduced row echelon form with ones down the main diagonal from left to lower right and zeros above and below the ones. Okay, we want to get 1 in the upper left hand corner. We want to use the 1 in the first column to get zeros below it. We're going to get 1 in the second, we're going to get 1 in the second row, second column. We're going to use the 1 in the second column to make the remaining entries in the second column 0. We're going to get 1 in the third row, third column. So A, B, C, D, and E is just row echelon form. Okay, so we're going to get 1 in that third row. Now, F, we're going to use the 1 in the third column to make the remaining entries in the third row column zeros. So we're going to go back up to the top. We're going to use that one to put zeros in the third column on the first and second rows. And then we're going to continue this procedure as far as possible. So what we're going to do is put ones. So basically you're going to have an augmented matrix. Before that vertical bar, it looks like 1, 0, 0, 0, 1, 0, 0, 0, 1. So that lower diagonal is zeros and the upper right is zeros. So this one just requires a little bit extra steps. Now some people would argue, and I think that's probably right, this is probably more trouble than it's worth, okay? Because the Gauss-Jordan method is basically requires a lot more row operations. If we just put it in row echelon form as we did before, we find that z, all you got to do is go back and put it back into the other two equations to find the remaining variables, and you're all done. Here, they want zeros in the upper place there. But you're like, what's the advantage of this? Well, the advantage of the Gaussian-Jordan method is it eliminates back substitution. I'll say it again. It eliminates back substitution. You're like, why is that? Well, if you have zeros everywhere except that main column, that z would be that one that left that third row. So z would be whatever that number is. The row right above it, you'll have the 0, 1, 0. So it's y equals to whatever is over there on the other side of the vertical bar. And then on the first row, you'll have 1, 0, 0. So the y is missing, the z is missing, and you have a 1. So x equals whatever's on the third row, the right side of the vertical bar. So it's easy just to determine what x, y, and z is immediately. So x equals that, y equals that, and z equals that. So that's the advantage of the Gaussian-Jordan method. The thing is, people would argue, and I think they have a good argument, is it's not worth it because the row operations do take a little bit of time, and you'd be done quicker if you just do the back substitution. So take it for what it's worth, okay? So, and then we're going to use the reduced row echelon form of the matrix in step 2 to write the system solutions set. See, and it says back substitution is not necessary. Okay, that's the advantage of the Gaussian-Jordan method. Okay, so let's do an example using this one. Now, it's the same example I did a while ago. Okay, solve the following system using the Gauss-Jordan elimination. So it's the same exact system. 2x plus y plus 2z equals 18, x minus y plus 2z equals 9, x plus 2y minus z equals 6. Same one. So if you remember, we have already solved this system using the Gaussian elimination with the back substitution. But when we simplified the system to the matrix, it gave us this row echelon form, remember? Okay, at this point, we didn't know what the x, y, and the z were. Well, we knew what the z was. We know z equals 3. But we didn't know what the y and the x was at this time. Okay, we had to go back substitution to determine that. But here's what we got to do here. This is how the Gauss-Jordan is different from what we just did. See the 1, negative 1, and the 2 in the first row, second and third columns? Do you see the negative 1 in the second row, third column? Those all have to be zeros. See, the lower left are 0, 0, 0, not lower left of the diagonal. The upper right of that diagonal, negative 1, 2, and negative 1 needs to be zeros as well. Once you get that, then you have a diagonal of 1s, and you have zeros everywhere else. And so therefore, you can identify the z by inspection, z equals 3. You'll be able to identify what the y equals by inspection, and you can identify the x, what that is, by inspection. Okay? So we will begin our work from this step. All righty. So we have 1, negative 1, 9. Okay, so what we're going to do is we're going to replace row 1 of this one by adding row 1 to row 2. So we add those up, we get 0 and 1, which is 0. 0 and 1 is 1. And then negative 1 and 1 is 0. And then negative 1 and 2 is 1. And 9 and negative 1 is 8. So we're just adding the first 2 rows and then putting it in the first row. Then what we're going to do is we're going to replace row 1 by multiplying the negative row 3 and then add that to row 1. Okay, so if we do that, we get, 0 times negative 1 is 0, add that one, still 1. Okay, 0 times the second element in row 3 is still 0, add that to the row 1, it's still 0. And then multiply the 1 in the third row by negative 1, add that to 1, and you'll get 0. And if you take the 3 and multiply it by the negative 1, you get negative 3, and add that to the 8, and you'll get 5. So now you have zeros. You're like, what? Now, wait a minute, whoa, it's 1, 0, 0, 5, isn't it? Remember what x was? X was 5, wasn't it? So now the only thing, we're not quite there yet because we don't have it in Gauss-Jordan elimination. We don't have zeros all the way. So we take that 1, 0, 0, 5, 0, 1, negative 1, negative 1, 0, 0, 1, 3. And what we're going to do is replace row 2 by taking row 3 and adding it to row 2. So 0 plus, remember the first row is already what you want, and the third row is what you want. So we're going to add the second row to the third row. So 0 plus 0 is 0. 1 plus 0 is 1. Negative 1 plus 1 is 0. And then negative 1 plus 3 is 2. And so once we get it in this format, this is called Gaussian-Jordan or Gauss-Jordan elimination method. And if you notice, the 5, 2, 3, remember that 5, 2, 3 was my order triple, that was the solution? Look on the right side of the vertical bar. 5, 2, and 3. So x equals 5, y equals 2, and z equals 3. So you don't require any back substitution. But again, people argue with this like, yeah, okay, that's fine. But I would have been done already if you just allowed me to do back substitution, and there's a case for that. So, but I needed to teach you guys this technique. And, to be quite honest with you, I'd never used the Gauss-Jordan method. I was taught it myself, and I did it for exams. And when they told me to do it that way, they say use the Gauss-Jordan elimination method to solve this system. I did it. But if I ever had to solve a system and I have a choice, I would just use the Gauss elimination method and put it just in row echelon form and be done. And there actually is another technique. It's called the Cramer's rule. And I'm a bigger fan of that one than any of these techniques anyway. We just haven't got there yet. The Cramer's rule is a little sweet. So, okay. Okay, so the last matrix corresponds to x equals 5, y equals 2, and z equals 3. And so the solution set is 5, 2, 3. And so it's the same answer. So, alrighty. Now, again, we've done 2 techniques to solve systems of linear, 3 equations with 3 unknowns. So when that happens, you can do it by the substitution, the elimination method that we've learned before, or we can do it by the Gaussian elimination method, and that's where the zeros in the lower diagonal, or we can use now the Gaussian-Jordan elimination method, which is zeros in the upper and lower diagonals, which is what we just showed you here. Okay. Now, understand, not every system has a solution. Not every one of them has a solution. Sometimes there is not a common solution. So if you ever get something like a row that has all zeros in it, you like 0, 0, 0, and maybe there's a 4, 0, 0, 0, 4, then that means 0 equals 4, and that would be false. That would be a no solution. Okay, so therefore that system would be inconsistent. So while you're doing your row operations, when you're doing your row operations and you ever encounter a row that has all zeros in the augmented matrix, except there's a number on the other side that's not 0, then that's an inconsistent system. So don't be surprised that could happen. Another possibility is if you have zeros all the way straight across the board on a row, like there's a 0, 0, 0, and a 0. In that case, the system is consistent, but it's a whole plane that's the actual solution. And so therefore, the equation, basically what you have to do is let z be a particular variable, plug that into the other one, and so every ordered pair is basically a part of another variable. So it's basically an equation format. And if we encounter that one, we'll cross that bridge when we have to. But most of these systems will have an order triple. Okay. Occasionally you'll have a system that's inconsistent, and that's probably a little bit more common than the third possibility, which is what I just explained about a plane being the answer. So basically, when a system is inconsistent, you'll get 0, 0, 0, and 7, or some other number like 4, or something like that. And that's a contradiction, because 0 cannot equal that number. So that system would be getting inconsistent. But then there's every so often you'll get a system that is the whole plane is the answer, and it's 0, 0, 0, 0. They're all zeros. And so therefore, that's another situation. And if we encounter that one, we'll talk about it when we get there. Okay? So that one's a kind of a tough situation to deal with. So, alrighty? All right, so that concludes this one. And if you have any questions on that one, and if you do encounter one of those systems that does appear to be either inconsistent, email me. Let me know. Let me share that with the rest of the class. Okay, so that would be nice for me to get that equation and say, hey, wasn't this one what you were referring to? And I'll say, oh yeah, you're right. That's one that's inconsistent, and I'll do it, and then I'll just upload it to the rest of the class. And hey guys, here it is. It's just this slides didn't actually have one of those. And by the time we show you every possibility, the video is about 2 hours long, and you're bored to death with it by then. So we try to keep these as short as possible. That's sometimes impossible to do, though. So, but anyway, so yeah, if you encounter something that doesn't look right as far as being consistent, like maybe the system, like I did end up with zeros on one of those rows, and that shouldn't have happened. What do I do with that? Tell me which problem it is in the book. I'll look at it and say, yeah, you're right, and send it, and I'll send you a solution to that, and give everybody else a heads up. So you'll be doing everybody else a favor as well. So, okay. So if you have any questions, like I said, do that. And we only got a couple more videos in the Math 136 class. We got a lot more to do in Math 138, but we have just a few more to do in Math 136. So 136 is we're getting close to the end. 138, you're about almost halfway through. So, all right. So, you have any questions? Like I said, see you, and I'll see you on the next slide, next video, and you have a good evening.